Hi, and welcome to the first video in our series, where we take you behind the scenes of what happens between submitting your Tiny Tapeout design and receiving your chip about 7 months later. Every 6 weeks, we'll update you on the journey, showing you key milestones and helping you prepare to test your design once it arrives. In this first installment, we're going to look at combining all the designs, running final checks, and sending it off to the semiconductor factory, otherwise known as a fab or a foundry. As you probably already know, your design is one of hundreds on the same chip. That means you'll be able to explore lots of other designs, as well as get your design tested by other people. Not only that, but it also helps to keep costs down. The more designs we can fit on one chip, the cheaper it gets. When you submit your design, it's actually already run through some tests, because we include some in the GitHub Actions. This job is called the pre-check, and it runs some Tiny Tapeout specific checks. For example, it's the correct size, and it doesn't use the top metal layer. Afterwards, it also runs the foundry's rules, like the design rule check, or DRC. The job of the DRC is to check the chip is actually manufacturable by the fab. If the shapes are too small or too close together, the machines in the factory won't be able to make it. Submitting your design opens a pull request on the chip's repository. That's a fancy way of saying that you've made a request that we update the chip with your design. Before we can merge your design, a new set of tests are started, similar to the ones already run on your single design. Sometimes a design passes the pre-check DRC, but putting two designs next to each other will cause the chip's DRC to fail, because two structures are now too close. It's important to pass DRC, because if we don't, the foundry will refuse to make our chip. As you'll see later, one of the manufacturing steps grinds the wafers extremely flat, so it's important that the average density of the wafer doesn't vary too much. To achieve that, we run a program that fills all the empty areas with little squares. The size of the squares and the spacing between them keeps the density where we need it. When your design is enabled, it needs a way to talk to the outside world using the chip's limited number of pins. To make that possible, we use something called a multiplexer, or a mux. You can think of the mux like a very fast switchboard. Even though hundreds of designs share the same pins, only one design is connected at a time. When your design is enabled, the mux connects your inputs and outputs to the chip's pins and disconnects everyone else. Each design also has its own power switch. This protects the chip from problems like short circuits by making sure that only the enabled design is powered on, while all the others are completely disconnected. That way, even though many designs share the same chip, each one can be tested safely and independently. That actually takes quite a lot of work to make happen. Each design has a power switch, so it's only on when it's enabled. Then there are the inputs, the outputs, and the bidirectional pins. With up to 512 designs, that's more than 10,000 wires, and they all have to get joined together into just 24 IOs. We run a set of tests that simulate the designs being enabled and sending signals through the mux. We also use a type of formal mathematical proof that proves that no two designs can ever be enabled at the same time. Then we create a ROM, or a read-only memory. That contains the chip's name and the git commit of the repository. When you plug the dev kit into a computer, the Commander app can read the ROM to figure out which chip it is and to fetch a list of all the designs inside. Here's what the final chip looks like. It's full of different size designs, connecting to the multiplex arms and then onto the I/O pads of the outside. We put the git commit as text on the actual chip layout down here, and the Tiny Tapeout logo up here at the top. Once submissions are closed, we take the final version of the chip and send it to the factory. We currently work with 3 different factories, and the processes are slightly different for each one. Regardless of the factory, our chip is one of many that will be manufactured on the same wafer. This is called a multi-project wafer, or an MPW. It's another way to reduce costs, where multiple companies' designs are produced together. About 40 different chips are joined together into one block, and then this block is repeated across the whole wafer. When the wafer is finished, the chips are cut out and each customer receives only their own design. Because we're sharing the wafer with other companies, we only get a few hundred chips back. But the upfront cost is far lower than producing a wafer dedicated to just a single design. For the IHP 130nm process, the factory has its own MPW service. After we submit our design to them, they combine it all together with the other projects. Many factories don't run their own MPW. They outsource it to an intermediary like Chip Foundry, Waferspace, Europractice, or Moses. They do the work of talking to the customers and combining all the designs together before sending the finished file to the factory. After that, it's time for the factories to get started, and we'll be getting dressed up and washing our hands to visit the IHP factory in the next video. While you wait, take a look at your chips page on the Tiny Tapeout website. Which design is yours? When you get your chip back, which other designs do you think you'd like to try out? If someone else wants to try your design, will they have enough information to test it? Okay, that's all for now. Thanks for watching, and I'll see you in the next episode.